Morning. Welcome to Krishna's classroom. This talk is a repetition of what I did yesterday. In yesterday's lecture, so happened that the audio was not clear. Therefore, I am re-telecasting it. There may be some changes accordingly. I hopefully it would be better than what I did yesterday. So let us start with see what I want to do is we have previously looked at the Banach theorem, the statement of the theorem, and some of the preliminaries for that is what we are going to. We are essentially going to enter the proof of the theorem systematically. Now we had been spending a lot of time on linear functions and their geometric interpretations, and there is some little thing to get for the completion. Now let me take the following. X is a norm. Now I am taking X as a normed linear space. Over a field K. K is real or complex. So if it is R, then we call it a real vector space. If it is C, then we call it a complex vector space. Now, what we designate with small f is a map from X to K and as you know, f is called a linear. We designated by NF the null space of that is set of all vectors x belonging to x such that fx equal to 0. And then we were looking at this one, the quotient space structure. And this is a fascinating space. Okay. What we have proved is that NF is a maximal proper space of X. By which you mean, of course, if it's a proper subspace, then there exists some Y which is not in NF, and we take NF, so there exists a Y X slash. Note this is X slash NF, that is, it is there in X but not in Y, or I will write it not to confuse between the two notations. Y belonging to X, Y not in F such that span of X union enough, right? This is what we mean by a maximal proper subspace, and this is also called a hyperspace. This is another terminology that. Okay. So what we have proved is, and the consequence of this is that since NF is a maximal proper subspace of X, see that you have X by NF is a one dimension Now, this is the result that we have proved already, and you see that X by NF all those this is what we have proved, and where this stands for set of all y such that X plus Z y Z belonging to this is the notation. And some of the fascinating structures which are not obvious are that the facts that we have is the following, that any X where y a chosen element of that is element which is in X but not in NF, comma X prime belongs to NF and K is an element of where X prime they are uniquely this is a nice representation. Okay, so here X prime belongs to F. That means f of X prime equal to 0 and K is a scalar belonging to the field and it is uniquely determined. This is the important thing. So this is a unique representation, nice representation theorem. And as a consequence of this theorem, we have proved the following. We have proved the following. The x is equal to is, and what we have is this. The union is disjoint. This is because, see, x1 we can prove this, f, and this is the fascinating result that we could do about this. And we have already seen the manifestation of this. In R2, a maximal proper subspace is a line passing through the origin. So call this M is equal to some NF. Now you choose a vector y belonging to y not in NF, and then you can, what you can show is that take the whole of the linear space spanned by y. So one dimensional space. Now you take what is x, bracket x. Bracket x is right. This is some k. So bracket x is the line parallel to M. Bracket x is the line parallel to M passing through K. Parallel to M passing through K1. That is, you have x equal to x prime plus K. However, this is the case. So you see that by varying k, you can write the whole of x here is the union of parallel lines. So This is a disjoint union. These are parallel lines. Lines parallel. So this is what we have. Okay. Therefore, now what we claim is that this is the case. So this is the case whenever f is not equal to 0. This is NF itself. Okay. Right. Now we will prove this theorem. F equal to 0, it is trivial. Okay. And f is not equal to 0, then we have already that. Okay, we have to consider the set of all. So consider we have already seen that these special properties are valid, and we can define. So here what you have is and this, of course, you can show that a y right? X prime belongs to null space of A. Okay. And therefore, by definition of this collection, see that this is equal to so this is another example. This is because you can show that x minus ky is in NF. because that's how we have taken. Okay. So you have x equal to x prime plus ky x minus ky and of course k comes out and this is equal to, that's easy. Now we prove the following, find addition. So on scalar multiplication, alpha x. So these are the definitions of. Now obviously the question might come that are they well defined? Here are they well defined? This is the question. One can prove that if this is easy because if x1 is equal to x1 tilde and x2 tilde equal to x2, these two are satisfied. That means x1 minus x1 tilde belongs to NF, x2 minus x2 tilde belongs to NF. Therefore, x1 plus x2 tilde, x1 tilde plus x2 tilde minus x1 plus x2 belongs to. Okay. What it means is this. Why you want to verify this? You want to verify this to make sure that irrespective of what representative elements you choose, because these are a collection of elements, what representative elements you choose, compute the sum, you end up with the same box. That is the point. Similarly, this I leave it to you. It's the usual stuff. This is because alpha y, that is alpha x minus, just verify, that's all. X minus x1 belongs to NF. NF is a subspace, therefore alpha times that belongs to NF. That shows that the bracket alpha x is the same as bracket alpha x, which in turn means alpha of x equal to alpha of. So the sum and scalar multiplication are well defined. Now one can verify easily. I am not going to that. So verify that all the conditions are all the requirements of sets. That is, so you have to verify everything. In particular, the identity element, additive identity. Yes. So also F minus is the first additive. Now the verification of these conditions are okay. Therefore, what we conclude is that after proving all this, that we have, and this is what we stated. Okay. Now, what is the dimension of? And this is where the following note that if x belonging to implies such a y exists and x prime belongs to let a x prime and k y. Choose the uniqueness. Therefore, and what is the consequence? The consequence is that is the following. The consequence is this. Every x, this is true for given x, there is, and once y is fixed, k is unique. K is therefore you see that for any x, this is true for every x. So for every x, ky. This is okay. Therefore, what do you have? Which implies what does this mean? Spanned by a singleton set, that is seven dimensional. Also, now we talk about so all these statements do hold without the assumption that x is a normally unique space. Holds good. All that you need is X is a linear space over K. That's the only condition. So let us write that. Now we normed in linear space or so we define norm. That means you have X, we designate it by this. This is the normed space. Okay. Now we define the form. We rather I hope it is not confusing. It's the same bar here and not necessarily this. Now this we define as K times odd K times so this is X by this is the definition. Okay. Then assert that X by NF is this well defined? It's well defined. Okay. So we show that this is a norm. The first thing that you have to verify is equal to 0. That is clear from the definition. The second thing that you observe is that generally equal to 0, that is dependent. Therefore, what does it follow? So this so that is the outcome. Now we have to verify the two things, namely the homogeneity and the what you call triangular equality. Now we claim that following This is okay. What does this mean? See, x1 equal to x2 equal to k2. Okay. Therefore, I'm skipping some steps, and you get a1 plus 1. Therefore, it's by n. So what does this mean? This is less than or equal to by nf, and this is of course equal to what is it? Norm of x1 I have skipped some steps. They are obvious. Now the fourth property that we have to verify, the fourth property is that explained. So this is what you have, and this is essentially one alpha norm of so it's a norm. So hence it's a norm. So that we have proved. Now what about the f? What is f of x? F of x equal to for which, since f is linear, it is f of x prime plus k times f prime. Here, and this is equal to k times okay. So and this is used in the reverse direction, namely that once you have a proper subspace, so we can have the following result. And y not in x is a fixed vector, then f is determined by m and f of is rather right a scalar, say alpha, that is f of determined as alpha So rather I can strengthen this. That's quite easy. That is the crux of results that we have so far on the structure of null space of a functional. So essentially, a linear functional determines a maximal proper subspace as its null space. Conversely, if a maximal proper subspace is given, then by fixing the value of the linear functional at some y which does not belong to x, once y is chosen, defines a unique. That's it. Okay. So this is what we have, the sum and substance of what we have. Now we can have what is norm of f is defined by the usual value. So of 1. Okay. Now a remark that this is the same. So this is also equal to supremum of, I say, norm x equal to 1. This is the definition of the norm of which we shall require while working on the Hahn. Okay. Now we state the Hahn. Normed linear space x, and if f is a bounded linear function, so I have to say what is bounded linear. It's f extend a linear functional f on x such that okay, let me just insert something here which I should have said, that definition if such that norm of f sorry. F is a bounded linear function on X if there exists an M positive such that modulus of Fx is less than or equal to M times norm of X. Okay. So in that case, you can see that norm of F is bounded by M. Okay, and the supremum of that over this is essentially X. Okay. So we'll okay. So this is the statement of the norm of F is equal to. So this is the statement of the unbalanced. That means the following. Let me just qualitatively explain what it is, or schematically explain what it is. Suppose this is X, then norm. The norm will be X. Now suppose M is a proper subspace. So this is again, so M is also a norm-bending space. M is a proper subspace of X. Now F is a map from C to this is K. K is either R or, and this is F. This is assumed to be linear. So this is linear on. Then what it says is this, that there is a map from the whole space to this, from X to this, designated by capital F, such that F restricted this is equal to F. And F is a linear function. And you know that the norm of F is finite. Therefore, and this having the property that norm of F is a norm-preserving state. It's a norm-preserving state. Okay. Now I will make some remark about this in the context of R2 after proving the theorem, because then it will be much better. Okay. Now we will prove this theorem in due course. And as a preliminary work for this proof, for developing the proof, let me just state another thing. For that we need some little bit of some definitions. Make the following observation. Note that every complex vector space is also a real vector. For instance, C over C is a complex vector space, or Cn over C is a complex vector space. Okay. Now Cn over R is also a vector space. Okay. But now it is a real vector space, because the field that we work with is the real field. So the difference is that the first statement has C as associated, and in the second statement R is the. Okay. Structurally there is some subtle difference, because you know that Cn is n-dimensional over C, whereas Cn is 2n-dimensional over R. So as vector spaces, structurally they are different. So that is the, so it's a complex vector space. Whereas say 2n-dimensional so it is also a real vector space. So Cn is a real vector space, but then structurally it is this. This is C plus C. So we make the following definition. A complex linear function on a complex vector space X is a map phi from X to C which is linear. That is phi of here X belongs to now we also define what is a real vector space. Or a real linear. Okay. Now on complex vector space X say is it's a real valued map from on X is X is really that is F or I write phi whereas phi is X and phi of for every X belonging to X, alpha belonging. So this is the difference from the earlier scenario. Okay. And this is, of course, we are now talking about a real valued function and not a complex value. So these are the two. Phi is a real value, whereas here phi is a complex value. This means phi. Now X may be complex. Now you see that we can talk about the real part of a complex valued map and the imaginary part of a complex value. Okay. So let us work on it. And are they real linear functional? Suppose that is then the question that you ask is U a so that is the question that so the following theorem complex complex linear space. That is, it is a linear space over C. Then the first statement is that U is the real part of F a complex linear function on X, then it's a beautiful representation. Okay, that's the first part. The second part is, if U is, that is the reversing this, U is a real linear function. X, which is a complex vector space, and if F is defined by one, then F is a complex linear function on X. See, this is the most interesting aspect. That is, X is a normed linear space. The other two statements do hold without the assumption that it's a normed linear space. Even without norm, they are valid. But here, we are now assuming X is a normed linear space, and F and U are related by statement 1. See, here what is happening is that the advantage of this result is this: you can work with real linear function and prove the entire Hahn-Banach theorem on the real linear function, and then make an application of this result to extend it to the complex linear function. Okay, because this is a very striking feature, namely that this is norm preserving. Okay, the norm of U is the same as the norm of, or norm of F is the same as norm of U. So you get a norm preserving complex linear function from a real linear function, where both the real linear function and the complex linear function have the same. Okay. So this is a very useful result. It's a very simple result though, but but it's very profound. So this is I want to display this again. This is the representation that, or the relation between complex linear function and the real part of it. Okay, right? Clearly, once f is given in this form, then its real part is q. Okay, and vice versa. So this is a connection between. So the real part essentially determines the complex linear. Okay. So that makes our working on the proof of the Hahn-Banach theorem a lot simpler. To the first part. So you let z be a complex number which is of the form alpha plus I. So that alpha is real z, imaginary. Both are real numbers. Okay. Now you immediately see that Iz multiplied by I, this becomes I alpha minus, whose real part is minus beta and the imaginary part is alpha. Okay. Right? Therefore, minus beta is equal to so we shall use this result. Therefore, what is the implication? The implication is this. It's very easy to get this now. From this, you observe that so what? Real part of Z is alpha and the other part is I times what is imaginary part of Z is real part of. So we will mark this. Now we come to what we want to. So we want to work on real part of if fx is a complex number, then we are simply writing this. So take z equal to then real part of I times fx equal to what is it? See, f is a real it's a complex linear function and therefore I can take this inside. So this is equal to real part of f of ix since it's a complex linear function. And this, of course, by definition, this is 2 of forget about the argument is ix. Even when then f of ix you take and then okay. So you go for the real part of it. The real part of it is so f of ix is 2 of ix plus I times p of ix. Okay. So that we calculate and we make use of this. Therefore, this is equal to of ix, and consequently, to what we get when this is equal to plus f is a complex linear function. Therefore, to see that I of fx is essentially the same as f of x. Okay. Therefore, this you write as x minus, and real part of f of ix is 2 of ix. So this is equal to minus I times, and therefore we have the following representation. So we have proved A. Okay. And this is the statement of the. This is essentially what we call. Now let me prove this. U is a real linear function on B, and f is defined by this expression. Now we have to show that complex unit. So we have this following: fx is equal to okay. So f of x plus y, this is essentially u of x plus y minus I of x plus y. Now this is equal to ux Now this is actually writing that out, and then you see that y minus I. Therefore, this is equal to so it is additive. That is what it is. Now we have to prove that f of alpha x equal to alpha of x. Now here alpha belongs to C. Okay. So sufficient to prove that if you prove f of okay, so let us prove this. So what is f of x? This is equal to u of ix minus I times of ix, which is equal to u of I into I square is minus. Okay. Now you see this minus can come out because it is real. It is minus 1 into, so it can come out because it's a real linear. Therefore, this is equal to of plus, this minus comes out, so you get plus here. Okay. So this you can easily see that this is equal to I times I times f of x is I times x plus u of, so this is u of ix plus I times x. That is I times x. Look at that. Now the next statement is about the norm, which is norm preserved. Assume then mod ux is less than or equal to mod f of, that is clear because fx is equal to 2x, or what is that? You have that representation, fx equal to so this is the real part of it. Okay? The absolute value of the real part is less than or equal to the absolute value of the complex. So if this is the real part of it. The real part, the absolute value of the real part is less than or equal to the complex. That is obvious. And suppose you take norm of u. What is norm of u? Norm of u equal to what? This is this. And norm of taking the supreme norm on both sides, you have norm of u okay. Now we have to get the reverse inequality so that you have equality. This is probably the simplest part. It's always true. It's very easy to see. But the other part needs some kind of insight. Okay. Now, for every x, to prove the reverse inequality, now you see that fx is a complex number. Which implies there exists a complex number alpha with on alpha equal to 1 such that see, whenever fx is not equal to 0, this is obvious. Whenever fx is not equal to 0, we find okay, right? Then see that this, so this exists. So okay, so this is the proof that so this is real. Okay. So mod fx is equal to alpha fx. So this is equal to alpha fx. f of alpha x, and this is equal to see u of alpha. Now this is the point. See, this is real and is equal to mod fx. Therefore, it is the real part of it. That is the reason for it. Okay, this is the real part of it. Therefore, mod fx is less than or equal to norm of u to norm of alpha x. This is equal to norm of u to norm of alpha x is essentially norm of x, because mod alpha is this is equal. That is the reason. Okay, what does this mean? This implies take suprema models. So you get norm of f. So you have two inequalities. Norm of u is less than or equal to norm of f, and norm of f is less than norm of. The significance of this is that you can get a complex linear functional from a real linear functional without changing the norm. And this is something that we are going to talk of our thing. So I hope this time it is very well heard, and there is no problem about that. And I had to repeat the whole thing because later I discovered that I didn't use the microphone at the time of lecture. So that was my mistake. Sorry for the trouble. Thank you very much.